Good afternoon. My name is Clay Wygant. I'm the presenter today of this major educational webinar. Today's application is on mobile mapping for tunnel systems. And it's about the repeatability and the reliability of the results that we can achieve. What we'd like to talk about to get started for this slide is the overview of mobile mapping in tunnels. And what are some of the challenges that we're facing? In a tunnel environment, mobile LiDAR systems, they work extremely well in the open sky, roadways, where we've got GPS. But in areas void of GPS, it requires an awful lot of attention to the work that we're doing. Without a GPS signal, we end up with a tremendous amount of drift or can, and that's just something that we have to be prepared for. And so it's kind of a dead reckoning rather than a fixed solution. And so somehow we have to correct up for these anomalies that we see in the data. And so we're going to be correcting the trajectory, the positional data associated with the LiDAR, so that we can get it into some kind of a form or format for design and construction specifications. So this is, so in mobile mapping in tunnels, these are some of the challenges that we face every time with the system, with GPS conditions, with degraded, of a degraded signal, which creates drift, which alters the true and actual driven trajectory, and then correcting up for all of these situations. So some of the parameters, we've listed about 7 parameters here that are part of every survey that we would do mobile-wise. And so we have it kind of split up into open sky conditions and GPS denied conditions, like we would see in a tunnel. So the dynamic driving, we usually perform this in an open sky condition, and it's very difficult to do in a tunnel, especially on rail. But dynamic driving is a way to kind of wake up the inertial measurement unit and perform some movement of the system, because the system wants movement to correct and to find its be in the correct position for our collection. The GPS signal is something we always have when we're out in the open sky condition, and we never have it in a tunnel, because you lose GPS obviously as soon as you go into a tunnel environment. The DMI is a distance measuring instrument. It's a velocity measuring. There's a possibility of putting it on a rail vehicle and obviously on a road type vehicle for open sky conditions. It's a method that attaches to the wheel. So you have to, it wouldn't work on a train car, but it does work on a vehicle wheel. And we weight that to help with the solution of when the system is idle or moving. And I believe that the DMI is a good use in that instance, where it's tightening up the solution when the system is still or moving. We have a base station that everything's tied to, or a course network, and that doesn't change whether we're in an open sky condition or a tunnel. We have controlling targets, and this is more dependent on the type of survey that we're performing, but the controlling targets are part of the operating parameters in most cases. Conventional survey, we can use them in both situations, open sky or in tunnels. Obviously, there's conditions and safety conditions to think about in both of those that are somewhat different. And sometimes there's leveling through points, and this again ties into what the basis of the project is, and what the control accuracy standards are. These are some of the parameters that go into the operation. So what we're trying to do in a tunnel environment is correct the trajectory and the trajectory process. So without the system being initialized properly, and that comes from a lack of GPS, and you can see in this image that we're looking at here. You would have no GPS in this image, and so we're trying to pay some additional attention to the trajectory functions. And we do this in a few ways. Sometimes there's known geometry of the track if we're in a tunnel with in rail. There'd be as-built, CAD type as-built, or on a roadway. And then the geometry data, there's some kind of an alignment. Those are very handy and would be quite useful in the process of correction of the trajectory. Sometimes we can go out and collect that information if it's not available. So you could do some additional collection of the track geometry, possibly using an Amberg railcart process. Or you may possibly just get some ancillary controlling data. And that's a kind of a visual objects, something we can see in the scan, and something we can measure in the environment. In either case, the trajectory is going to be enhanced by this additional information that can be provided. It's a little bit on the trajectory correction process. What we at the Maser Consulting call this is, we call it the M-fix, or the Maser fix. This is partly a non-provisional patent pending process. It has a lot of moving parts, but the M-fix is something that we apply to tunnel mapping procedures. It's part of the procedure. The M-fix utilizes mobile LiDAR. It's what it's built around. The M-fix includes ancillary control. So we were talking in the last slide, different types of geometry or static information. And it could be, in the image identifiable objects would be those ancillary pieces of information that we could measure. And the M-fix enhances post-processing procedures. So now that we can accurately fix the trajectory within this non-GPS environment, it creates a repeatable and reliable results. So we call the process the M-fix, the Maser fix. We'd like to talk about some example projects, a couple of things that we've performed in the past. We've selected 3 for today. There's one here that's the Amtrak East River Tunnels in New York City. It was about 2 miles in length. Tricky because it dead ends and you have to back out. So there's no daylight on both ends of the tunnel, only on one end. So that's difficult. It's obviously rail. It's an older tunnel, and this is a good example of it. The second project would be the Eisenhower and Johnson tunnels in Colorado on I-70. It's out west of Denver. It's very high. It's the highest piece of interstate in the country, highest tunnel, I believe, in the country at 11,000 feet. And so we're going to talk a little bit about some work that we performed for a consultant on the Eisenhower tunnel. And the third project would be the Washington Metro system. This was a very challenging environment. We want to discuss why we were working there and some of the products that we delivered out or captured out of that. But you can see a very long series of tunnels there. Let's go to the Amtrak and the East River Tunnel and look at that for a moment. So the tunnels were being revitalized because of the Superstorm Sandy. That was a major flooding event. The tunnels were completely flooded in the middle of things. There was some substantial damage, and they're trying to figure out how to, refurbish these to a state of usage that they could get another, I'm not sure what the time frame is, but probably another 50 years out of it. Our mission was a very, very accurate survey, 800ths of a foot absolute accuracy. So it's going to support track mechanical and overhead and catenary type systems that are going to be replaced and redesigned. So there needed to be some very accurate work done. The systems deployed had a very heavy conventional survey application to this. We needed a fair amount of control. We used the Amberg system, the rail geometry system. I think both in a measurement of the rail mode and in its capacity to capture three-dimensional data of the tunnel walls and the environment itself. We obviously used the Regal LiDAR system. And this is a good example. I mean, it's a very integrated system. The picture of it here has a series of, fixed focal directional cameras, ladybug camera, dual sensors, and GPS. And then we applied the Maserfix in the post-processing, and that was part of the solution, or the reason that we could create such an accurate representation of that tunnel system. The systems themselves have a very sophisticated inertial measurement unit in them, and we've utilized that in conjunction with our Maserfix to create this product that can be relied upon. So the tunnel in the East River tunnels, there were two of them that we stored, and both came out very repeatable at the beginnings, where you can actually measure the data together. We have the Eisenhower Johnson tunnels. The project revolved around this fire suppression system that was being designed for the tunnels. There had been an accident. I'm not sure if it was within that tunnel system or another. Colorado, I believe, has more tunnels than any other state in the union. But a fire in a tunnel is a devastating thing. So there was no fire suppression system, and there had to be one built. So the mission was to create this very accurate representation of the clearance envelope, because somehow we had to measure horizontal and vertical clearances, anything that was protruding from the walls or the ceiling, and then how much room there was going to be to bring down from the plenum space some kind of a fire suppression system. So the systems deployed on this, we had multiple different systems. The conventional survey was a big component. The survey targets were not deployed in the drivable tunnel at all. They were placed up in the plenum space in the utility. In this tunnel, probably most tunnels, the part that we drive in is just part of the tunnel. The other part is overhead, and usually it's got the air vents and the fire suppression system, all the utilities. A lot of that runs in that area, and that's the case with the Johnson and Eisenhower tunnels, because there's a large plenum space. So we deployed the Leica team with the Leica C10. They worked their way from one end of the tunnel to the other in the plenum space with the control that was provided, the conventional survey control. In the end, we actually ran the mobile LiDAR through the tunnel and captured the tunnels. So there was no traffic control necessary to do the capture or the control, which is very positive. And then, we deployed an incredibly inventive method of controlling the mobile LiDAR. So in the plenum was the control and the scan data. There was a series of vents that were visible top and bottom. So from the quality C10 static scan data, we extracted valuable point data on the vents, the vent system, and used that in controlling the mobile LiDAR. So that was a unique project and a very innovative method of controlling the data. So that's the second project that we thought would be of interest. And here it shows a distance measuring device, this velocity measuring device that's on the wheel of the vehicle. This would be the third project that we wanted to basically review a bit. In the metro system in Washington, there's over 100 miles of tunnels. The one we were talking about was a 26-mile stretch. The mission was that we needed to have a 1 foot absolute accuracy. So when we talk about absolute accuracy, it pertains to the project control. So it's about project control, the absolute accuracy. So our mission was to support this telecommunication design and construction, and we had to do quite a few clearance checks in order to get to that point. And you can see on the wall here, it's been designed and it's been overlaid in the scan data, what the brackets would look like, and then where the cable is laid. And so at this case, you could, when we did, send a vehicle car through and look for clash detection would be the term. So the systems deployed on the metro project were conventional survey crews. They placed targets along the alignment for us to use in the adjustment of the mobile LiDAR. We ran the mobile LiDAR system through all 100 miles of tunnels. We relied heavily on not just the conventional survey that was done, but also the mathematized alignments and the ancillary track information that was gathered by the field crews. This was very, very important in this environment where the dead reckoning was very difficult to manage. And we developed this maser fix, the M fix, during this time period as a method of a better way to deploy and adjust the project data. It includes many components, and these are a couple that are right in here, the mathematized alignments. And in some instances, agencies don't have that, some they do. In this case, WMATA had a great deal of legacy data that was available to us. Those are the projects that we see. There are some alternative methods of data capture for a tunnel, and we've worked all of these options. One is a static, tripod-mounted scanning system. They're extremely accurate and quite economical and a good approach for some real specific applications. Usually it's a distance, size of the project, but very good choice of tools. The second one would be an Amberg trolley or some kind of a geometry trolley similar. So the Amberg trolley is very, very precise rail geometry measuring device. It's really a grand option for clearance and site condition assessment. And this is a good example of one here. It looks like I'm not sure which station this is. Another alternative method would be to apply the mobile LiDAR to an actual vehicle of the line. And that we would be using for a broader network data capture, as I would call it. The work could be performed during revenue periods rather than waiting for flagger and more safety people at night. So you can work between scheduled trains, and that's very, very handy. So sometimes this is an alternative that works, doesn't always, but you can see right here, this is a very, very unique setup. You don't get all of the images that you normally would because the train is in the way here, but you can picture the system capturing the imagery from the back of the rail car, and beyond. There are three decent alternative methods to data capture. That's the short story on mobile LiDAR in a tunnel environment. We'd like to open up the webinar to a couple of questions at this time. So if you sent a chat through, I think Maria can read some questions to us.
Hi, Clay. Yes, thank you. We have a few questions. The first question we have is from Sean, and the question is, how much control is necessary when mobile mapping a tunnel?
This is a good question, and I think the amount of control necessary is really dependent on the accuracy requirements of the project. But real typically in a design type environment, in a tunnel, we place targets in the 300 or 400 foot range, and then we add some of this ancillary information, and it might be something as simple as a corner of an electrical box or a corner of a doorway. There are lots of image identifiable objects within the tunnel. So that would be basically I would call it this. In a design environment, I would be 300 to 400 feet and some additional information.
Oh, thank you. Another question is from James, and his question is, can you overlay objects within your scan for check for clearance? Say you want to check if a double stack train can fit within your current single tracked tunnel.
This is another good question, and I believe Maser Consulting has done that exact project or something very similar to that, and utilizing multiple tools. So yes, you could. The way I envision that would happen is you need some very, very good track geometry. So that probably relies on some Amberg information, the Amberg geometry trolley or the track, probably the mobile LiDAR to get the overall view of the environment, and then you could build the double stack and send it through, and then but highlight the areas that are in contact, and then create a design off of that. The one we did, I believe they ended up cutting a little, two, looks like bat ears out of the ground, out of the tunnel for these double highs to go through.
Okay, thank you, James, for that question. Another one here is from Dan, and his question is, what is the minimum track time window necessary to collect data?
You know, often if we're on a high rail, you know, it's usually the third shift. Very often, unless we're on a train vehicle. So a 2.5 hour window is probably the minimum, I would think, and that's usually obtainable with you know, the authorities. So within 2.5 hours, it depends on the length of the track then, and the put on and take off locations, because usually once your time is up, it's really close to time for revenue if you're on a track.
Okay, thank you. A question from Carol is, what is the average cost of tunnel collection?
You know, people always want to know the cost, and I understand that completely. It's something that I think is very specific to specific projects. I think I would defer that to maybe a follow-up, you know, a personal follow-up email and discussion. That would be my best bet on that one.
Okay, very good. And it looks like there's one more question, and this question is from Tom. Can you share the control between the mobile system and other survey instruments?
Yes, so it's going to start off, the control would start off in a conventional manner, usually, some kind of a conventional manner. So you could share that with the static crew, which could use the same points and densify a specific area and do some static scanning off of the same control, tying the two products together. Same thing for the Amberg data. They could densify for the uniqueness of what they need. And so the answer is yes, and it's a real positive approach as well.
Okay, great. Thank you, Clay. I think that concludes the question and answer portion of the webinar. So I guess I'll hand it back over to you for any last comments or best ways to reach out to Maser.
Okay, I think on the thank you, Maria, and I want to thank everyone who participated today. Questions and polling, and for your time. I mean, we're all busy. There's survey webinars at maserconsulting.com. is a good way to get in touch with us and send any question or inquiry that you might have to that address. And we can conclude with this. The tunnel, I guess I would conclude with the tunnel scanning with mobile LiDAR is a very unique process, and we have figured methodology into this that creates really repeatable and quality results. And so we'd like to share that with you in a broader way. So please contact us, reach out, and we'll be glad to discuss further. So again, thank you for your time today, and that concludes today's educational webinar.